Our final speaker is James Sinclair. James is currently a warfare analyst for the United States Navy. He has been an expert in the field of air-to-air combat for 17 years and has authored numerous papers for symposia such as the Military Operations Research Society and the Combat Identification Systems Conference. Mr. Sinclair holds a master's degree in physics from Texas A&M University, where he studied supersymmetry and cosmology. Prior to that, he received a bachelor's degree in physics from Carnegie Mellon University. James, come and let's welcome him as he does.
Yeah, I think you got that information off the blurb for the Blackwell Companion, and it was old when it was put on there. I've actually been in the Navy for 23 years now, so God help me if we lose the next war. I think it's my fault. So, okay, I am a modeler by trade. I'm employed by the United States Navy. My field is artificial intelligence and the creation, maintenance, and analysis of results from sophisticated models of air combat. I work with teams of subject matter experts, each an individual expert in their field, much as Dr. Carroll is an expert in cosmology. So I don't stand in relation to this problem the way that he does. I'm not a cosmologist, but what I am is a knowledge integrator who interviews subject matter experts and tries to put them together into a holistic whole, a model. Now, the model builder or knowledge integrator has to know the inherent limitations that come from answers provided by subject matter experts. To answer a question requires a context, a world of its own that intersects with the real one, but only imperfectly. Our models may reach for a conclusion that is a mere artifact or limitation of the tool set, or the conclusion may be sound. The problem of the artifact applies to cosmology, specifically in the role of the prediction of a singular beginning to the universe from Einstein's relativity. I'm going to focus on one narrow topic, Kalam's second premise, as Dr. Craig introduced last night, which is a claim the universe began to exist. And as you learned last night, this premise has two components. Does the universe have a beginning, which is not quite the same claim, and what is the nature of time? I don't have time to talk about time, so I'm going to deal with the first issue. Now, models may intentionally not have internal entities within them that correspond to structures within the real world. There may not even be an internal structure. Models of this type are called instrumental. For example, suppose in my field I wish to build a model that determines if a missile impact destroys an aircraft. Such a model may be a sophisticated physical model of the missile fusing and impacting an aircraft with lethal projectiles. A vulnerability model is built for the aircraft that specifies the location of critical subsystems. Against this is applied the physical prediction of the impact pattern of the warhead fragments. From this comes a prediction of the probability of lethal damage. On the other hand, I could just take some dice and roll them. Certain numbers would represent a kill, others survival. The second model is purely instrumental. Not only does it not purport to have internal entities that are representative of reality, it has no internal entities at all. The first model is an attempt at a realist model. In between, one may have effects-level models that don't strive to model all physics processes explicitly. Model tool sets are elastic, have high and low fidelity parts, and are usually in analyses telescoped to focus just on the particular question one has in mind. We must interpret every result for its true significance, or lack thereof, in this light. Now, in the world of cosmology, there are many tool sets. Let me suggest three categories. There are Einstein's equations within the general theory of relativity, hereafter GTR. There's a set of more speculative and competing tool sets within the rubric of quantum gravity. And there's something that I will call GTR plus, which are Einstein's equations with corrections informed by considerations from quantum gravity. GTR and the singularity theorems. Over the last 10 years, I've approached many cosmologists via email for the purpose of interviewing them on the models they've built. In fact, Sean Carroll has been gracious enough to be in a dialogue with me for the last 2 weeks before this conference. Most cosmologists will talk to you. They love education. They love educating the public. Now, it's remarkable they'll talk to you considering how busy they are, and the only thing in it for them really is the joy of teaching. Now, when we approach our subject matter expert and ask her to school us on cosmology, she may first speak to us about GTR. Imagine GTR like a set of Legos. The possibilities for building worlds are endless, but there are some rules. There can be time machines in GTR, universes that lack a global definition of time, and universes that expand in one direction while simultaneously contracting in another, like a taffy puller. Our subject matter experts usually restrict themselves to something called Friedman, Robertson, Lemaitre, Walker spacetimes, because such spacetimes closely match our empirical observation of the universe we actually live in. Such spacetimes are nearly homogeneous, isotropic, have a global definition of time, and aren't time machines. You know, how boring. One of the main things about GTR is that there are some natural stopping points for the worlds one creates. Within GTR is the concept of world line. A world line, also called a geodesic, is the path through which an observer such as yourself passes through space and time. Even if just sitting in a chair, one is still tracing out such a path. Normally, these world lines are said to apply to freely falling particles under the influence of gravity. When cosmologists speak at the public level, they might talk of an astronaut in a spaceship with the engine turned off. Imagine a universe filled with astronauts. We should like to know their past and future. In GTR, these paths may trace to past or future infinity, or they may wrap around in such a way that a time machine is created, or the past or future may be truncated. It is this last possibility in which we're interested. A world line that stops short of infinity is an indicator of a pathological condition within a GTR spacetime, called a singularity. These singular pathologies can exist to the past or future. They may be local anomalies such as a black hole, or it could be a global temporal feature that signifies a Big Bang origin or a big crunch. It's the curiosity of an observer literally ending existence when one reaches the end of a world line or beginning to exist at a world line's origin that initially interests us. From the 1960s to the present, GTR theorists have been probing these space-time pathologies with the use of mathematics. Does the universe, for example, have a beginning? I'm just going to mention one of these theorems for time, and it will be the 2003 theorem of Arvind Borda, Alan Guth, and Alexander Vilenkin, who hereafter BGV. But let me explain a little bit more about what it actually is. They derived a novel result that suggests the past of an expanding universe likely, but not certainly, has a global temporal boundary. What they did was start with the fact that observers sprinkled throughout an expanding universe are flying further and further apart. Now take a light beam and consider its future as it is observed by subsequent observers. The fact of the expansion has the effect of the observer seeing the light red-shifted at later and later times. BGV considered what would happen if you looked to the past and what spectators in the early universe would see. They were able to show that the world line of light was inextendable to an infinite past because the light would then be blue-shifted to a degree that violated conditions of relativity. Similarly, they considered what would happen if the same set of observers saw a drifting spaceship. Later and later in the history of the universe, the observers would observe the relative speed of the drifting ship at smaller and smaller velocity. But as one looked to the past, the spaceship would appear to be faster and faster to these earlier and earlier observers until the novel effects of approaching the speed of light were encountered. BGV took this to mean that there was a past boundary to an expanding cosmos. A conservative way of stating this would be to say there is either a beginning or some completely different type of physics takes over. There's a suggestion in their original paper that there is a quantum-based beginning of the nature of Vilenkin's own tunneling from nothing proposal from 1982, which is very similar to the Hartle-Hawking model that Dr. Carroll presented yesterday. Now I want to take a step back for a moment and talk about a problem called rhetorical gloss in public speaking. Consider the French philosopher Paul Valéry, who warned us, "The simple is wrong, but the complex cannot be understood." Therefore, how do you communicate? There's a temptation, especially in public speaking, to guard against this latter threat and thus grab the other horn of the dilemma, which I've been guilty of myself. Oversimplification can also come in in this case, by not explicitly speaking to all caveats and underlying assumptions. Just don't have time. Thus, as the speaker oversimplifies, as I'm about to do, and later critics of the speaker, I think, err if they claim that the speaker was unaware of this or that caveat. I don't know how to solve this problem, but I do know that discussions of the BGV theorem are particularly vulnerable. So I'll just say this about BGV. It is an important result, but it is not a silver bullet or a soundbite. Understanding its significance requires a context. In fact, the whole subsequent discussion of BGV's new physics at the boundary leads to a whole different layer of complexity, which I'm going to try to speak a little bit to in my final 30 minutes here. So next topic, diachronic emergence, GTR plus, and the treatment of time in quantum gravity. Our subject matter experts tell us that the past temporal boundary predicted by many GTR models could be representative of a breakdown in the toolset. As such, one wonders whether the prediction is just an artifact or is still a pointer toward a genuine beginning for the universe. A good article to read about this type of problem in physics generally was penned by Isaac Asimov some years ago and is entitled "The Relativity of Wrong." Asimov warns against the fallacy of rejecting a model result merely because one may expect that eventually a model paradigm will be replaced by a different one. Asimov tells us that paradigms do get replaced, but the replacement is usually just an incremental improvement in accuracy over the old one, even if the nature of the physics could be completely different. Thus, while Newton gave way to Einstein, and Einstein will give way to quantum gravity, it's a terrible error to throw Newton away and claim that he was just wrong. By the way, I'm not accusing any of the scholars here of making that error. Newton was not far wrong, Einstein was less wrong than Newton, and quantum gravity is promised to be less wrong than Einstein. But if wrong is just wrong, then we can't even trust quantum gravity or whatever's going to follow that. Can we learn nothing about the cosmos? I think we can. There's clearly something wrong with throwing away the predictions of a theory just because another paradigm is on the way. What we wonder then is whether the Big Bang singularity is just an artifact of GTR or whether it is a true indicator of a beginning that will be better described in quantum gravity. Just because Einstein will be overcome doesn't mean that he should be thrown away. And I'm not saying anyone is trying to do that. Now, our subject matter experts tell us that the concept of time is well known to be problematic within quantum gravity. Some theorists even believe that time does not really exist. Now, staying relentlessly within the rubric of the Kalam cosmological argument, for now I'm simply going to take time seriously in the sense of the tensed theory of time that Bill Craig mentioned last night. And I'm going to examine three different options coming from 1993 up to the present about how some people have looked at time and quantum gravity. The first will be a generic quantum foam. So what happens at the singularity? Here are two popular level descriptions, one strictly from GTR and another taking a step forward into the realm of quantum gravity. Yes, they're popular accounts, but they'll help us think. One must be careful of the aforementioned problem of rhetorical gloss in considering a popular account. Some things may not be meant literally. But by talking for the public's sake, the theorist is forced to think in terms of literal cosmic evolution. There literally is matter in motion. The universe is a thing that endures and undergoes real literal change. Now, in both of these accounts, the author's speaking of an astronaut falling into a black hole. What happens to the astronaut? We'll start with these descriptions and then extend them into a discussion of a past temporal singularity. In GTR world, physicist Robert Garrick tells us the following, quote, "There is no event available on the singularity itself to the astronaut. In particular, there's no possibility for a future extension of the astronaut's world line after he hits the singularity. What then does the world line of an astronaut hits the singularity mean physically? Mathematically, what happens is that the world line just stops. Physically, this would mean that the astronaut is snuffed out of existence. After some finite time, according to himself, he ceases to exist," end quote. On an evolutionary view of reality where matter really is in motion, an astronaut would literally cease to exist. Remarkably, there's not even a final moment of existence. The singularity is a boundary to space-time, but is not within space-time. Now let's take this one step further. Here's a description I find illuminating of an approach to a quantum foam. The description from 1993, but still relevant, again relates to an astronaut falling into a black hole. Physicist Kip Thorne tells us, quote, Einstein's equations predict that as the astronaut reaches the singularity, the tidal forces grow infinitely strong, and the chaotic oscillations become infinitely rapid. The astronaut dies, and the atoms from which his body is made become infinitely and chaotically distorted and mixed. And then at the moment when everything becomes infinite, the tidal strengths, the oscillation frequencies, the distortions, and the mixing, space-time ceases to exist. Just when does quantum gravity take over, and what does it do? As best we understand in 1993, quantum gravity takes over when the oscillating tidal gravity becomes so large that it completely deforms all objects in about 10 to the minus 43 seconds or less. Quantum gravity then radically changes the character of space-time. It unglues space and time from each other and then destroys time as a concept and destroys the definiteness of space. Time ceases to exist. No longer can we say that this thing happens before that one, because without time, there is no concept of before or after. End quote. Thorne gives us a lot of rich detail that supplements Garrick's GTR account. What is of interest to us is the prediction of the destruction of time. In order to bound our problem, we're going to imagine this is literally true. We're going to put a stake in the ground to help us think. Let's turn the clock around and imagine emerging from the singularity. In GTR world, we can tell from Garrick there's actually no first moment, yet one nonetheless begins to exist. That's bizarre, but that's the physics. Looking at the problem from Thorne's quantum point of view, there would literally be no time associated with a quantum foam. In the foam, time is destroyed and space is indeterminate. So what could it mean to say that a quantum foam would precede the classical phase of the universe? Let's think now about the whole universe and a possible quantum gravity temporal origin. One of the right questions to raise relates to Thorne's correct observation that without time, there is no concept of before or after. Many quantum gravity approaches suggest that the space-time background ceases to exist at the fundamental level. But if the quantum gravity era has no time, then it's impossible for it to be a primordial era, earlier than the classical universe. This I refer as the logic problem of diachronic emergence of classical spacetime. What might this mean? The implication is that a quantum foam serves as a past boundary to the universe, but is not actually a state of the universe. In this manner, it functions similar to a singularity in GTR. One might expect that the best physical model would be what I have described as GTR+. There are quantum gravity-inspired corrections to Einstein's equations. There may be an era earlier than GTR itself may predict, but there could be a beginning just the same. But if one doesn't allow space-time to be destroyed in a quantum gravity approach, something like BGV might still apply. In personal communication, Alexander Vilenkin told us this about these GTR+ models. He said, quote, if fluctuations, quantum fluctuations, are not so wild as to invalidate classical spacetime, the BGV theorem is immune to any possible modifications of Einstein's equations which may be caused by quantum effects. End quote. This tends to bound our problem for us, even though it doesn't fully solve it. If spacetime is literally destroyed by quantum gravity, there seems to be a beginning. But if spacetime isn't destroyed, there may yet be a beginning if an incompleteness theorem like BGV still points to a temporal boundary. Next topic, imaginary time. The problem took a serious turn into the philosophical realm when in 1993, philosopher Quentin Smith observed a related problem to the one I just pointed out in quantum foam with a prominent attempt at quantum gravity, the Hartle-Hawking no-boundary model. In this model, Hawking and Hartle appear to suggest there is a primordial era for the universe which features imaginary time. In this era, time would act exactly like a spatial dimension. It is supposed that there eventually is a classical era with ordinary time. The actual mathematics are much more complicated for this model, though, and include a mathematical technique called the Feynman sum over histories. In quantum terms, there's a superposed wave function that generates a probability of the ultimate emergent universe being of a particular form. This model, and a related one from Alexander Vilenkin called the tunneling from nothing model, is also sometimes presented as a topological transformation from nothing to a four-dimensional universe. But is imaginary time a primordial era? This is where Smith disagreed with Hawking and takes him to task. Smith says this, I quote, "Clearly Hawking is offering a physical interpretation of four-dimensional space, that is, Euclidean spacetime. But such an interpretation is implicitly logically self-contradictory. The problem appears in the statement that the four-dimensional space joins on to real normal spacetime once the quantum smearing effects subside. The question then arises as to the geometry of the four-dimensional space, which has to somehow smoothly join onto the more familiar spacetime once quantum smearing effects subside. If the four-dimensional space does not possess a real-time value, how can it stand in relation to the four-dimensional spacetime of being earlier than it? If four-dimensional space is not in real time, then it is not really earlier than, later than, or simultaneous with the four-dimensional space-time manifold. Accordingly, it is false that the four-sphere joins onto the familiar space-time, that is, after in real time. Quantum effects dissipate. Nor can Hawking's term once refer to the imaginary time, which would imply that the real space-time is later in imaginary time than the four-sphere, which it is not. There is no imaginary time in real space-time, and real space-time is not located in imaginary time." End quote. But we have to be careful. Is Hawking's use of the term once just rhetorical gloss? Well, in 1996, philosophers Reid Guy and Robert Delteet formally followed up on Smith's suggestion and reached a similar conclusion regarding both Hawking and Hartl's no-boundary model and Alexander Vilenkin's tunneling from nothing model. They analyzed the apparent temporal claims made in the Hawking-Hartle model in premise form and found the premises not compatible. Guy and Delteet's conclusion was that, quote, "emerging from imaginary time is incoherent," end quote. This doesn't end the story, though. For in 1999, Jeremy Butterfield and Christopher Isham clarified the issue for many by establishing emergence in a synchronic rather than a diachronic sense. Synchronic being bottom-up emergence as opposed to a temporal relation in time. They do agree with Smith, Guy, and Delteet, yet they take him to task as follows, I quote, "A considerable philosophical as well as popular scientific literature about the emergence of time has grown up around Hawking and Hartle's proposal, but we believe that much of the literature is marred by not taking significant cognizance of the problem of time which besets the Euclidean program. In a nutshell, by ignoring the problem of time, much of the literature makes it look as if the no-boundary proposal treats the emergence of time as a process in time, that is, according to the temporal sense of emergence. And then, unsurprisingly, the no-boundary proposal seems to face conundrums and contradictions," end quote. So Butterfield and Isham argue that the typical diagram used to describe the HH universe, which Dr. Carroll, I believe, had up last night, where the bottom of a cone is rounded off, showing an apparent join region between imaginary time and classical time. They say it can be misread, even though Stephen Hawking often uses that diagram. Butterfield and Isham seem correct. There doesn't seem to be a temporal relation between the imaginary time mathematical structure and the classical Lorentzian universe when you evaluate Euclidean models in detail. Therefore, Butterfield and Isham's remarks seem to lead toward the embrace of an instrumental interpretation of the Euclidean imaginary time geometry. Now, perhaps one could embrace a realist interpretation of the topological transformation picture where nothing transforms to a 3 dimensions of space plus 1 dimension of time classical universe, and I'm tempted to go that way myself. On such a view, physics and mathematics have difficulty conceptually modeling the concept of creation ex nihilo, or creation from nothing. So when the universe emerges from nothing, nothing is actually modeled as a transition from something to something, where a dimensionless point plays the role of nothing. I believe this is an interpretive difficulty and could actually point to an actual ex nihilo origin for the universe. And I believe Dr. Carroll last night did offer that that model did have a beginning. And I want to make one interesting point. You know, what do Victor Stenger, Dr. Lawrence Krauss, Stephen Hawking, James Hartle, and Dr. Carroll have, and myself, even though I wouldn't put myself in that august company, what do we have in common? We all like this model and believe that it has a beginning to it. Now that should show you that the Kalam's second premise, at least the part of it that says the universe has a beginning, that is a theologically neutral statement, as Dr. Craig indicated in his talk last night. Now treating the non-classical physics instrumentally or embracing the topological transition picture still seems to lead us back to where we were in my generic quantum foam picture. The earliest era of the universe treated in a realist ontology is something like a GTR plus model, in which case we still have a beginning. Next, let's move all the way up to the present and talk about a common strategy to deal with time in quantum gravity, use of a separate degree of freedom to play the role of time. Some years ago, I queried cosmologist Martin Bojewald on this issue, an expert and proponent of loop quantum gravity. He indicated the following, quote, "It seems to me that the conclusions you sketch are based on a severe truncation of the cosmological model, as is commonly used in quantum cosmology. One analyzes the simplest case where it is essentially only the spatial volume which is left as the lone degree of freedom. This is what Hartle, Hawking, and Vilenkin did. But I suspect that this truncation is the reason for your conclusions of incompatibility. In general relativistic systems, one cannot formulate evolution with respect to an absolute time, but one can do so relationally. This requires the presence of suitable degrees of freedom, such as matter fields, which allow one to map different points in space-time to different values of the degree of freedom. In this case, the matter field can serve as a measure for time, which is pretty much what we actually do when we measure time with a clock or by looking at planets or stars. Many quantum cosmological considerations, however, are based on truncations where such degrees of freedom are simply removed by hand. This simplifies some technical calculation, but makes the interpretation of results more complicated." End quote. So Bojewald suggests that the Hawking, Hartle, and Vilenkin methods are primitive, and the approximations used in building them may indicate that the truncation of time indicating a beginning may indeed be an artifact of failure to consider a more realistic condition with more physical degrees of freedom. In the specific case of loop quantum gravity, the method resolves the GTR singularity by discretizing space in a complicated way, and its mathematical forms are difference equations as opposed to, say, differential equations. Many loop quantum gravity attempts at cosmological models suggest a before the Big Bang era. Studies usually pick something like a scalar field, or the matter field that Dr. Bojewald talked about earlier, to play the role of time and map the volume of the universe on either side of the big bounce in something like a cyclic model. The use of a physical degree of freedom to play the role of time in the theory is generic to many proposed quantum gravity tool sets. This can lead, though, to interpretive difficulties of its own. For example, Martin Bojewald has recently argued that the bounce events of a cyclic model could represent a scenario similar to arrow of time reversal models, such as, for example, Carol Chen. He suggests that measurements of the state of the universe after a bounce might be unusable to derive knowledge of the state of the universe before the bounce. Information is lost through the bounce. Thus, the model contains what Bojewald calls cosmic forgetfulness as a salient feature. An observer just before the bounce would find that attempts at predicting the post-bounce future suffer from this cosmic forgetfulness. Bojewald interprets this as having reversed arrows of time on both sides of the bounce. So in his view, loop quantum gravity does not necessarily show a before the Big Bang history. Rather, it could show two expanding universes coming away from the high quantum region. Now, would a quantum gravity resolution of the GTR singularity produce past eternality? Bojewald suggests it might produce a reversed arrow of time on the other side of the boundary. But, and this is where the philosophy of time comes in, and where, for example, you see Dr. Craig and Dr. Carroll disagree. It's really there that the difference is that I believe they have in interpreting these models. On Dr. Craig's view of time, moments on one side of the boundary are in no sense earlier than moments on the other side. And therefore, there isn't an infinite past, because since the moments aren't earlier than say, the classical universe, then it's not the past, because the moments aren't earlier. Another objection to the interpretation of a before the Big Bang in loop quantum gravity cosmology comes from cosmologist Heinz-Dieter Zeh. He objects to the interpretation of loop quantum gravity models as having a unidirectional arrow of time. In fact, in the same volume that Dr. Bojewald gave the cosmic forgetfulness model and his reversed arrow of time approach, Heinz-Dieter Zeh says this in a different essay. He says, quote, according to arguments used in loop quantum cosmology, the Wheeler-DeWitt equation, and this theory replaced by the difference equation with respect to the scale factor of the universe, a measure of how much the universe has expanded, can be continued through the bounce region to negative values of the scale factor. The configuration space of three geometries is in this way duplicated by letting the volume measure assume negative values, which is conceptually like turning space inside out as you go through the big bounce. So its continuation would then have to be interpreted as an enlarged superposition of components that are individually experienced as expanding universes. That's actually very similar to what Dr. Bojewald was saying if you have two universes that have a reversed arrow of time, although I don't think this is exactly the same concept. Because where this comes from in Heinz-Dieter Zeh's work and with his colleague Klaus Kiefer as well, they use something called the WKB temporal approximation. And they say that there are quasi-classical trajectories that are representative of universes that are like general relativity. But in such an approach, these classical times cannot be continued backwards through a big bounce, where the WKB approximation breaks down. So he says the following: the interpretation of negative values of the scale factor is highly questionable. So the interpretation would be something like a causally disconnected set of expanding universes as opposed to a before the Big Bang model, which we could interpret as universes that have a beginning. Although I do want to be careful not to misrepresent the views of Dr. Zeh and Kiefer. I believe that their ontology, they believe that the realist ontology is the wave function and that these quasi-classical trajectories are the approximation. But if we interpret time similar to the way that Dr. Craig and I do, we would actually flip that ontological commitment and say perhaps the wave function should be taken as instrumentally and the quasi-classical trajectories should be taken realistically because they have evolution taking place within the universe. Lastly, Dr. Bojewald himself has highlighted another problem with this approach in quantum gravity. In a 2013 paper, Bojewald et al. Say this about this very approach. Quote, the problem of time remains unsolved, affecting the right choice of dynamics. The problem is usually evaded, but not solved, by using specific choices of global internal times, which tend to be unrealistic near the Big Bang, such as a free massless scalar or dust. As part of the problem of time, it's not known how to transform quantum wave functions or entire Hilbert spaces between different internal times, and therefore results found with one choice of global internal time do not necessarily hold for other choices. But if they depend on what time is used, they cannot be considered physical, end quote. Different choices, therefore, of the degree of freedom, if I have multiple choices, that represent the temporal dimension can yield different physical predictions for the universe. This seems especially problematic, as Bojewald himself has pointed out. What are the real physics? Now, in a personal communication with Dr. Bojewald a few weeks ago, he told me that this problem is generic in nature. It's not native to the specific paradigm of loop quantum gravity. However, perhaps the problem could be solved as Bojewald et al. Believe, and they continue to do work to show that there could be cyclic bounce models. But the method seems highly problematic, as we saw in the three examples, two of which Dr. Bojewald, as a good scientist, talks about himself. But if I need have no prejudice against beginnings, nor see, and why have them, because it's a religiously neutral statement anyway, nor do I see a necessity to have a full quantum gravity primordial era, where am I led? I'm again attracted by the idea that GTR plus models can capture the origin of clocks and thus capture the origin of the physical sufficiently for our purposes. So therefore, to conclude and summarize, what do we make of this? I think we're led in two radically different directions. If I embrace time as fundamental, by which I mean the sense that me and Dr. Craig take the tense philosophy of time, I seem led to something like a GTR plus model, which again, to reiterate, are quantum gravity-inspired corrections to GTR within a GTR framework. The very problems we see with having a temporal dimension in quantum gravity physics may be indicators toward a conclusion of a beginning to the physical, and perhaps time itself. Perhaps this comes in concert with the tunneling from nothing result, which one interprets as a genuine creation ex nihilo. Or perhaps I could believe in these quasi-classical trajectories that come from something like the WKB approximation as entities that compose a real multiverse which are all expanding. Therefore, one could summarize the options as follows. There's 5 of them, and the 5th is a break from the first 4. Suppose space-time doesn't break down in the past sufficiently to invalidate the BGV theorem, as Dr. Vilenkin holds as a live possibility. And he's my subject matter expert, and I listen to my subject matter experts. So, if so, that would still point to the possible global temporal boundary that BGV have entertained. Second option, all of space-time breaks down. In that case, we're talking about is literally destroyed. This option fails to be primordial because it lacks time. Similarly, option 3, time breaks down but not space. This option would also fail to be a primordial era for the same reason that option 2 does. The most interesting option is option 4, space breaks down but not time. On such a view, you could have an arrow of time reversal at a boundary, and that seems consistent with Kalam's second premise in view of a certain interpretation of the philosophy of time. Similarly, the Hartle-Hawking model can be interpreted itself as an arrow of time reversal model. It's often viewed as having 2 waves that are ingoing and outgoing, and if you look at them in terms of a thermodynamic arrow of time, as Victor Stenger has argued, it looks like a biverse. But the 5th option, one could drop my presupposition and in some sense deny my philosophy of time. In fact, theorists today are usually talking in terms of synchronic emergence. In fact, Dr. Maudlin is an expert in that area, which, as I said earlier, is bottom-up ontological structure with time acting perhaps similar to a spatial dimension in a 4-dimensional block, rather than a diachronic emergence, which would be the arrival of the metric time of GTR from some more primitive but still temporal entity. A breakdown of space-time and quantum gravity, and that on this view would not inform a discussion of a primordial era. Rather, it refers to the synchronica problem of how there can appear to be space-time. I think this leads to 2 subsequent debates. First, the meaning and the competition of a synchronic vice a diachronic view of the emergence of space-time. And number 2, we're led back to, I believe, what is the central question of this debate. What is the philosophy of time? What is time? Thank you very much.
Well, much has been made of the claim that whether or not the universe had a beginning or whether or not the universe is eternal is a theologically neutral statement. It's a physics statement. And that may well be true, but let me give you a potentially relevant factoid. If you go to Google and you search for Borde-Guth-Vilenkin theorem, 98% of the results are from theology, not from cosmology. Now, why would that be? It's not because cosmologists don't recognize the theorem as something true. It's that, number one, they recognize that it's only a statement about the regime in which classical descriptions of space-time are good approximations, not a full statement about the actual universe. And number two, cosmologists are not invested in the answer. Cosmologists are invested in knowing the answer. They want to know whether or not the universe had a beginning or not, but they recognize we're nowhere near being able to answer that question, and the BGV theorem doesn't get us very close to it. Whereas some theologians seem to be very invested in this, and therefore they make a big deal about the BGV theorem. I don't think that the tendency to sort of pick pieces of evidence that favor your position and bring them to prominence is something that distinguishes theists and atheists in any way. Atheists do that plenty of the time, but it does seem to distinguish the subset of theists who make a big deal out of the BGV theorem. Remember I told you about the Aguirre-Grattan model. This is a classical space-time model that is absolutely eternal, that obeys the laws of the BGV theorem, and would tend to be completely well-defined. It never enters the quantum regime. I asked for an explanation of in what sense that model is supposed to have a beginning, and I haven't yet heard one. There is the issue with the Aguirre-Grattan model, just as with the Carroll and Chen model, that there's a moment in time where the entropy is lowest. So in our conventional understanding of time moving away from the period of lowest entropy, there is a point in time to the one direction of time and to the other direction. We both call it time moving forward. But this, again, as I mentioned before, equivocates on the fact that there's no place for God to have created such a universe. So unless this universe is fit into our explanatory framework, we haven't really done our work here. But the real issue, and Tim Maudlin alluded to this, is that we all, physicists, theologians, people on the street, tend to reify the concept of space-time far too much. We live in a universe that is fundamentally quantum mechanical, and the notion of space-time is fundamentally classical. But it's so useful, the classical space-time notion, that we tend to try to fit it into the framework of an ultimate theory, even though we know that's not the right language to use. If you want to get right the fundamental rules of reality, you have to talk the language of quantum mechanics, the language of wave functions, and Schrödinger's equation. And you see this problem when James Sinclair quoted Quentin Smith. I can, to the extent that I can appeal to myself as an authority, I promise you everything in that quote by Quentin Smith was wrong. But I don't blame him, because he was probably reading papers by physicists who were extremely sloppy in talking about what their theories meant. Hartle, Hawking, Vilenkin, whatever it was. We tend to talk in space-time terminology even though what we're describing are wave functions and quantum states. The real answer is that it's not that there's Euclidean time at one point and real time at another point. What there are wave functions at all points. Sometimes you can calculate them most effectively by using Euclidean time methods, other times by real-time methods. Remember, I gave you a theorem, the quantum eternity theorem, which seems to tell you in an ironclad way that the universe should be eternal if it obeys the rules of quantum mechanics. I don't recall any of the folks on the other side of the debate referencing that theorem, but you might want to know, well, how is it even possible to have a universe that had a beginning given that theorem, if quantum mechanics is the right answer? Well, every theorem has a little condition. The BGV theorem says if the universe has an average expansion rate greater than 0. Sounds like a little technicality, but is actually crucially important. The quantum eternity theorem has a little condition that says if the energy of the universe is not 0. If the energy of the universe is 0, then there is no strictly defined notion of time. And that is exactly the condition that applies to the Hartle-Hawking quantum universe, the quantum cosmology universe that does have a first moment. In that picture, time is emergent, not fundamental. So as a cosmologist, I'm happy no matter which way it turns out, but I know that we're nowhere close to knowing the final answer. Thank you.
I'm going to resist the temptation to respond to Sean Carroll's remarks because that's Jim Sinclair's duty. But let me simply say that I was careful in my opening statement in the debate last night to present the Borguth-Vilenkin theorem as simply one of the most recent theorems that show that classical spacetime had to have a beginning. Remember the boundary in superspace, which is implied by that theorem. And then the question is that the beginning of the universe, or is there something on the other side of the boundary? If there is something on the other side of the boundary, that's that quantum gravity regime. And here, Jim touches on very deep philosophical questions about what is time, or what Isham calls the problem of time, and this notion of space-time as an emergent reality. There's a good deal of talk today in the philosophical literature about space-time as emergent. But as Rainer Heydrich explains, the notion of emergence here has to do with different levels at which physical reality is described. An emergent feature is one that doesn't appear in the description of reality at the fundamental level, but at a higher level. The difficulty is in these quantum cosmogonies, the quantum gravity era does appear to be temporally and causally prior to classical space-time, to the Planck time. And yet that is incoherent, as Jim says. You can't have diachronic emergence of time itself because you would have to already have time in order for time to emerge. So either you have to say that this is merely a synchronic emergence, that is to say that this quantum gravity description is a description of the same reality, but just at a deeper level, or maybe a microscopic rather than a macroscopic level. And in that deeper reality, you can get rid of the initial singularity. But it's still the same reality. It's just different levels of description. So if classical space-time is finite in the past, so must be the quantum gravity era. It's not as though the quantum gravity era can stick out before the classical space-time. That would be incoherent. It's just different descriptions of reality at different levels. Now, what we must not do, and this leads me to comment on Dr. Carroll's remarks, is I don't think there's any reason to prejudice the fundamental level of description as somehow more real than what is on a higher level description. I call this mistake fundamentalism. And I think that people like Dr. Carroll are guilty of being fundamentalists in this regard, thinking that because something doesn't appear on a more fundamental description of reality, say microscopic scale, therefore it is less real or even unreal if it appears on a higher level. And that simply doesn't follow. There's no reason to prejudice the lower level over the upper level. Indeed, I would say that time is one of the most evident realities to us, inescapably real. The reality of time is even more evident than the reality of the external world, because I could be a brain in a vat with illusions of an external world around me, but the stream of contents of consciousness in succession, one after another, is undeniable and inescapable. Even the illusion of temporal passage is temporal passage. So that the reality of time, it seems to me, is one of the most basic, undeniable realities of metaphysics, of ontology that there can possibly be. And if time doesn't appear on the fundamental quantum level, then so much the worse for the ontology of that level. Then that simply means that it doesn't capture reality fully, to speak of reality on that sort of a scale. If this quantum gravity regime is in some sense temporal, even though not classically temporal, then, as I argued yesterday for Maguire and Kehayas, it cannot be infinite in the past. A quantum state cannot endure forever doing nothing because it's unstable. It would either produce the universe from eternity if it's causally sufficient for it, or it would never produce it. But there wouldn't be any reason the universe, classical space-time, would appear just 13.7 billion years ago after having waited from eternity past before creating space-time.
Thank you, Dr. Carroll. It is a privilege to be criticized by you. Bill's been criticizing me for years, so I'm used to that. Okay, there's 4 salient points that I want to speak to. The first about the theologically neutral, you brought it up in the context of BGV. I'm pretty sure I could have gotten Dr. Vilenkin to hold up a sign saying it's theologically neutral, because he's told me that many times. But certainly I can't deny what you're saying about the Google. You know, it is of significant interest to people like me. As I said in my talk, the notion of incomplete geodesics is relevant to the concept of a beginning, but as I was careful to say in my discussion of model tool sets, we do have to be careful about a naive commitment to a particular tool set. And I think you're on board with me on that as per the discussion that we had ourselves in our email. One other thing I want to say, and this actually addresses a point that I think several of the speakers on this side made, with regard to, especially Dr. Maudlin, I believe he made this point, that with regard to the practice of science and whether cosmology has anything to say, whether there's the fact that there isn't certainty regarding this subject of a beginning, therefore we shouldn't make conclusions on it. Well, you see, in the realm that I live in, that we practice a very different type of science, but I think it's the way it's done is just as valid as what's done in academia. In my realm, you have to produce the best answer you can on a deadline, because there are decision makers who are making decisions on what's going to happen with building jets 15 years in the future that hopefully are going to save the lives of pilots. And the key thing is that those decision makers are going to make their decisions whether I help them or not, whether they get the critical input they need or not. I don't have the option to say, I don't know, just because the knowledge base is incomplete. I have to give them the best possible answer at the time using the data incomplete as it is, and being honest about it, about the error volume or different sizes of trade spaces or assumptions, limitations, and constraints. So I look at that type of topic from a philosophy of science perspective very differently than you do. I think that you have to give the best answer you can right now. And part of the talk that I was going to give that I had to cut out had to do with the fact that we're living our lives right now. I guess I'm disagreeing with Dr. Maudlin on another point. I very much believe that discerning the existence of God does help me make life choices. And I call myself the problem child of Christianity. I think even though it's true that, as Dr. Carroll pointed out, that Dr. Craig has said that faith, you're not argued into the kingdom of God, essentially. I believe that it's true. What I mean by calling myself a problem child is that I think that if you did have a universe that was created by God, there ought to be evidence of it. And the other thing, I believe that in the public square, that if we're going to deal with issues on as to whether religious truth claims should have any currency at all in the public square, the only information we have to share with each other is publicly available information, which would have to be reason and evidence. I can't show you my heart and say, look, I believe that I have the Holy Spirit. I have to share with you this public evidence. So that's another reason why I'm interested in generating that. I'm going to cede you the point with regard to Aguirre Grattan. Dr. Vilenkin has written papers on this. He believes that that model does have a beginning, but he uses what I would term an idiosyncratic definition of beginning. Now, however, I did talk to Dr. Aguirre, and he said, if I got him correct, that most of the geodesics do hit the boundary in his model, and that very few of them actually go to past infinity. And so I don't know whether that leads to a conceptual difficulty or not, or whether I misinterpreted him. But it's very important. When Dr. Craig spoke last night about the, how many, whether universe concepts that are past eternal are viable, I believe he was repeating what Dr. Vilenkin said at the conference, Stephen Hawking's conference for his birthday party in 2013. Dr. Vilenkin made that very strong claim. In the Blackwell Companion article that Dr. Craig and I wrote, what we said is that it was difficult to envision, not that it was impossible to envision past eternal models. So I would be willing to cede that point to you. And my last point, I'll have to stop. Thank you.